An ordinary user on your server just ran 10 lines of code. 60 seconds later, they're root. They didn't crack a single password. They just asked the Linux kernel to copy a few bytes. That's copy fail. Officially, it's called CVE-2026-31431. It scored a 7.8 out of 10 on the severity scale, which is high. And it sat quietly inside almost every major Linux distribution since 2017. Ubuntu, Red Hat, Amazon Linux. If you ran Linux in the last 8 years, you almost certainly ran this bug. So how does a request to copy a few bytes turn a normal user into the most powerful account on the machine? Let's slow it down. Your Linux system has a feature most people never think about. It's called AFALG. Think of it as a doorway that lets normal programs ask the kernel to do cryptography for them. Encrypt this, hash that. It's useful, and it's built right into the kernel, the core of the operating system that controls everything. Inside that doorway lives a smaller piece called ALGIF-AED. That's the part that handles a specific kind of encryption, and that's where the flaw hides. Here's the part that matters. Back in 2017, a developer added what's called an in-place optimization. The idea sounds reasonable. Instead of copying data to a new location to work on it, just modify it where it already sits. Faster, less memory, a small, clever shortcut. But that shortcut made an assumption it shouldn't have. It assumed the place it was writing to was always safe to write to. It wasn't. To understand why, you need one more idea: the page cache. When your system reads a file, it keeps a copy of that file in memory, so it doesn't have to read from the slow disk every time. That copy is the page cache. It's a stack of pages, like sheets of paper, holding the contents of files you've recently touched. Including files you're only allowed to read, never change. Now put the pieces together. The 2017 shortcut let an attacker point that crypto operation at a page in the cache that they should never be able to modify, and then write to it. Just 4 bytes. 4 small bytes dropped into exactly the wrong place. That's the whole trick. That's why it's called copy fail. The copy that was supposed to be safe wasn't. 4 bytes doesn't sound like much. So why does it hand over the entire machine? Because of where those bytes land. On Linux, certain programs are marked as special. They run with root powers even when a normal user launches them. The classic example is the command that lets you switch users. An attacker uses copy fail to write their 4 bytes into the cached copy of one of those trusted programs. They corrupt it just enough to bend it to their will. Then they run it. And the kernel, trusting that program, hands them a root shell. The golden crown, total control, no password, no brute force, no phishing email, just a normal user, a normal-looking system call, and a kernel that copied a few bytes to the wrong page. And here's what makes it dangerous in the real world. The attack is local. That means the attacker already needs some kind of foothold, a regular user account on your system. That sounds reassuring until you remember how many accounts exist on a shared server, a cloud host, a web application running under its own user. One compromised, low-level account, and copy fail turns it into root. Researchers showed it could be triggered with a tiny script, around 10 lines. It blends into normal activity because it uses the same ordinary system calls your software uses every day. That's what landed it on the government's known exploited vulnerabilities list, the KEV catalog. That list means one thing. This isn't theoretical. It's being used in the wild. So how would you even know? This is the part too many people skip. Picture the morning it drops. You're the admin. You don't see flashing alarms. You see small things that don't add up. A background service account that suddenly spawned a root shell. A user process touching the crypto socket interface for no reason that fits its job. A program that normally never escalates, escalating. Copy fail is quiet, but it isn't invisible. The signs are there, in your logs, if you know to look. An unprivileged process reaching for AF_ALG, an unexpected jump to root. A trusted binary behaving in an untrusted way. Detection here is about watching for the impossible. A user who shouldn't have power suddenly having it. Now here's the twist nobody expects. The fix wasn't some brilliant new piece of code. The patch didn't add anything. It took something away. The upstream kernel maintainers fixed copy fail by reverting that 2017 optimization. They deleted the shortcut. The bug wasn't a missing safeguard. It was a clever line of code that should never have been written. Sometimes the most secure thing you can do is remove the thing someone added to be fast. So what do you actually do? Today, not someday. First, patch your kernel. This is the real fix. The major distributions, Ubuntu, Red Hat, and the others, have already shipped updated kernels that remove the flaw. Update, then reboot, because a kernel patch doesn't take hold until you restart. Check your kernel version against your vendor's advisory and confirm you're on a fixed build. Second, if you can't patch immediately, there's an interim mitigation. You can disable the vulnerable module. Blacklist algif ared so it can't load. For the vast majority of systems, this changes nothing you'll notice, because the cryptography quietly falls back to standard libraries. No doorway, no bug. But treat this as a bridge, not a destination. Patch as soon as you can. Third, watch your logs. Set up monitoring for unprivileged processes touching AF/ALG, for unexpected privilege escalation, for trusted binaries acting strangely. Detection buys you time, even on systems you haven't patched yet. And step back for the bigger lesson, because copy fail is not really about one module. It's a modern mirror. Every optimization is a bet. Every clever shortcut trades a little safety for a little speed, and most of the time you win that bet. But the cost hides in the corner, sometimes for years, until someone finds it. Copy fail hid for 8. The defense isn't fear of fast code. It's patching quickly, watching closely, and remembering that the kernel trusts what it's told. Make sure attackers can't tell it lies. So, an ordinary user on your server runs 10 lines of code. 60 seconds later, nothing happens. No root shell, no crown. Because you patched the kernel, you disabled the module, and you were watching your logs.